let's get into this. This is 4.2 Riemann sums. And that's Friedrich Riemann, German mathematician, who kind of developed these theories. Of Riemann sums, adding up a bunch of rectangles under a curve to determine the approximations of the area under the curve, and then taking those rectangles to the limit of infinity to get the actual area. We're not going to go to infinity today. We're just going to do some Riemann sums, some basic ones. But a Riemann sum uses rectangles under a function to approximate the area under a curve. So Riemann sum uses rectangles under a function to approximate the area under a curve. Right? The area equals the sum from I equals 1 to n of f of x sub I times delta x sub I. This is our sort of equation for the Riemann sum, right? N, in this case, the n that we have up here, the sum of how many is how many, the number of what do they call them? Number of, they call them intervals? No, they call them something else. Number of, hold on, subintervals. Number of subintervals, yeah. We call them subintervals. Number of subintervals aka the number of rectangles. How many intervals you use to slice your equation into. N is the number of intervals. So you're adding up all the rectangles, right? You're adding up from 1 to n rectangles, however many rectangles you choose, your subintervals, or how many rectangles you have, and you're multiplying this part here, f of x sub I, is like the height of the rectangle, right? The height. And delta x here is like the width of the rectangle. And so you're finding these heights and these widths, and you're multiplying all those rectangles together, and then adding up, right? Multiplying these together, height times width, and then adding up all the different rectangles together to get the area. And that area represents the approximation of the area under that curve, which is what we call the integral. That's our integral, right? That area. I should say that all of these have an interval that you're approximating, right? So I should say approximate the area of the curve from A to B. I should say that there's an interval here where we look at the starting point and the ending point for our area. And this delta x here, delta x, is equal to the size of the interval divided by the number of rectangles, right? So this gives us the width. This equation here can help us figure out the width of the rectangles, right? So we take the range here from whatever our ending number is minus our starting number, the distance between the endpoints that we're trying to find, divided by the number of rectangles. That gives us the size of each rectangle, even subintervals of our rectangle. That's why we call them subintervals, because it's inside this other interval. So cutting it up into this many sections of this width. So let me show you what this looks like. So for example, you have a function here, some function here. This says height of rectangle. Oh, goodness gracious. Rectangle. So let's say you have an equation, right? Here's our function f of x, some curvy function. We have an interval from A to B. And I want to find the area under the curve from this A section to B, right? From this point to this point here in the function, from some A to B, right? I want to find the area under this curve. If I have, let's say, if n equals, let's say I want 5 subintervals, then I'm going to slice this into 5 pieces, right? So let's see, 1, 2, 3, 4. 1, 2, 3, 4, 5 slices here, 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 and here. Right, so this distance between the slices is delta x. Right, that's my change of width, right? This is x1, x2, x3, x4, and this end is x5 here. x0, 1, 2, 3, 4, 5. So I have all the distances here. And then my height, well, my height is going to be each of these different heights in my function. These are all the f of x sub i's, right? All these things are the heights. Right? All these, right? The heights here, this is f of x sub 1. This is f of x sub 2, on and on and on. Right? Dot, 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 on and on. So you have all these different heights and you have all these different widths. And so with that information, we can slice up this rectangle, this curve, into rectangles and find the approximate area of this interval, right? We can say, well, let's say I want a height like, here's my first rectangle here, here's my second rectangle, that's a little bit bigger, right? My third rectangle, also a little bit big, fourth rectangle, fifth rectangle. And I can use these rectangles here to find my area. These rectangles here, 1, 2, 3, 4, 5 rectangles, and I can use that to approximate my area. Each of these have a different f of x, different height. The widths are the same though. They all have different heights. So sometimes you get a little bit that's missing. Sometimes you're a little bit off because you're a little low. Other times you're a little off because you're a little high. But hopefully overall, if it's curvy enough, then the whole thing balances. And we can figure out approximately what the area is. All right. So that's our idea. So let's get into how do we do this practically. Well, first of all, let me tell you a couple things here. There are actually many different kinds of Riemann sums. A question I have for you is, in my first rectangle here, when I'm doing my rectangle here, I have two choices for the height of the rectangle. Right? In this first rectangle, I can either choose the left side of the rectangle as the height, or I can choose the right side of the rectangle as the height and go backwards. So Frederick Riemann, noticed this, and he said, well, there's kind of two choices here. I can do a left Riemann sum, where I have the left height, and I have a right Riemann sum, where I can do the right side of the rectangle height. So we have two choices for Riemann sums. Left Riemann sum, R sum, and a right Riemann sum, R sum. I'm approximating because I don't want to write the whole Riemann word. Left Riemann sum and a right Riemann sum. The left Riemann sum use the left edge height of the rectangle, and the right Riemann sum uses the right edge height of the rectangle. So we have a left and a right Riemann sum, and we can find different values, right? We can find the different sums using this formula here, where we take the heights and the widths and multiply them out and add them all together. Let me give you an example. This example, we're not going to use a function, we're going to use a table of values. From a table, we have our x values and our f of x values. Ooh. In the middle. 1, 2, 3, 4, 5. So 6 values. 1, 2, 3, 4, 5, 6. 1, let's go with 3, 5, 8, 11, and 12. And f of x, let's say this is going to be 2, and then 6, and then 9, and then 8, and then 4, and then 0. Some function, we don't know what it looks like, we just have a table of values representing some equation here, some function. Some table representing some function. I want to find the left Riemann sum. I want to find the area, approximate the area under the curve using the left edge, and then I want to do it in the right edge and see what the differences are, right? So if it helps you, you can draw a graph of this. If it's helpful, draw a graph. If it helps, graph it. If it's helpful for you visually to see what's going on, just make a quick graph. Let's see. X goes from 1 to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Doesn't need to be perfect, right? Fx goes from 0 to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Do an approximate graph. Let's see. 1, 2, there's a point there. 3, 6, there's a point. 3, 4, 5, 6 right there. 3, comma 6, approximately there. 5, 3, 4, 5, comma 9 up here. And then 1, 2, 3, 4, 5, 6, 7, 8, comma 8 right here. 11, and 11 is here, comma 4. And then 12, comma 0, like that. So you see, kind of the graph goes up and then down. We don't know exactly what equation it is, but it's some kind of 1, 2, 3, right? 1, 2, 3. You graph the whole thing here. You could approximate the function. So what we're going to do is we're going to find the left Riemann sum, and then we're going to find the right one. Find left R sum, and then we're going to find the right one. When we're finding the left sum, I should say here, I want to have find the left Riemann sum with n equals 5 intervals. I need to say how many slices I want. How many slices I want. I can assume that each of these is a slice, but I need to be careful and see what exactly the problem wants me to do. If it said I want 2 slices or 3 slices, I would have to skip over one. I go 1 slice here, 1 slice here, right? And I have to have another point, 1 slice here maybe. But I want to have 5 intervals using the table. So I have my 5 intervals are going to be, one rectangle is going to be using these 2 pieces. That's 1. And then 2 with these, 3 with these, 4 with these, and 5 with these. So you can imagine the rectangles like this. Here's rectangle number 1, rectangle number 2, number 3, number 4, and number 5. Right? And again, graphically, you can visualize it over here. Slicing like this. From 1 to 12, our interval from 1 to 12. When I'm finding my sums, when I'm finding the left Riemann sum, right, I need 2 pieces. I need to find, 1, find the delta x, or the width, and then 2, find f of x, which is the heights. And then multiply those all together, multiply and add them all up. Add them all up. So you're finding the widths, you find your height, and then you multiply and add up all the rectangles together. So my area is going to be, area equals. Let's do this piece by piece. First rectangle. First rectangle goes from 1 to 3. So that distance, or the delta x distance here, the delta x distance is going to be 2. From 1 to 3, right? That's 3 minus 1, that's distance of 2. So it's going to be 2 times the f of x I want to use, right? So my f of x, again, I've got 2 choices here. I have this left edge for my height, or this right edge for the height of my triangle. Since I'm doing the left Riemann sum, this is going to be my my height number 1, my first height, times 2 for the first rectangle, right? This is my width of 2, my height for my first rectangle. Since it's on the left side, I'm using the left edge of this first rectangle as the height, right? So my first height, my first rectangle, goes up to 2 to 3 like that. Whoopsies. Up to 2 and uses my height like that. Right, so maybe I'll draw these heights here. So all these different rectangles here. 3 goes to 4, 5, 6, 7, 8, 9, 10, 11. So my first height is this one here. I'm using the 2 height, the edge there. So there's my first area, right? Width times height. And then I add that to the next one. Next width, from 3 to 5, that's again a 2. 2 times my left edge height is this 6. Here's my next height at the 6 right there. So I'm drawing this rectangle here. Drawing that rectangle there. This is making sense, right? I'm using the left edge, right? You see how I'm having the left edge making the height from the left side. Next rectangle from 5 to 8. Well, that's 3. Whoopsies. Wrong color. That's 3. So plus width of 3 times the height of the left edge, which is going to be 9. And that's this height here. So this one's a little taller than the other one. That's fine. 2 times 2, 2 times 6, 2 times 9, 3 times 9. Plus my next one. 8 to 11, that's also 3. 3 times my left edge height is 8. So again, that's going to be this height here up to 8. Plus my last one, 11 to 12, that's a height of 1, width of 1. My height for this one's going to be a 4. I should say this is the left height. So it's going to be plus 1 times 4. So multiply all these out, add them all up together. You get your edge, your widths, and your heights. 2 times 2, that's going to be 4 plus 12 plus 27 plus 24 plus 4. Let's see, that's 8, 20, 47, 60, 71. Is that right? Angel, welcome. $71, is that right? Did I add right? Hopefully that's correct. 20, 40, 60, 71, yeah. So that's the left sum. Left sum. Left sum is 71. And again, we don't know if the curve kind of goes like, generally like this, if it's like a smooth curve, maybe it kind of wiggles around, we don't really know. But we know that this is our first approximate area under the curve here. Sometimes it goes a little bit too high. Right here it's a little too high. Here it's a little too high. Maybe sometimes it goes a little too low. But overall it gets a pretty good average, so 71. Let's do that same thing with the right Riemann sum. Find the right R sum. Again, we're using our same equation, same idea. The area is you multiply the width times the height. Find the right sum. So again, same idea, find the widths, find the heights, multiply and add them up. So the area is going to equal. Now the nice thing about this is the widths don't change. My distance here is always the same width. Like the widths don't really change. But which value I use for the heights are going to change. In the first case, I used all the left ones. Notice we didn't even use the last number here. That was not, let me draw my last rectangle. That was not even part of my equation, right? I used this height here. I used the 4 as the last rectangle, the 4 there. So I didn't even use the 0 in the last one. For the left sum, you use the left side numbers. For the right sum, you use the right side numbers. So for the first rectangle here, we have a width of 2, same as before, width of 2, times a height this time of going to be 6 for the right sum, right height of 6. We didn't use the last one because there were no more triangles, no more rectangles, right? We use this, here's one rectangle, we use the left side height, left side height, left side height, left, left, left. And we didn't need to use this last number because we already had a height for this rectangle. We already had this height. From the 4 here, that was the height of the last rectangle. So we didn't need to use the last one. In the right-hand side, we skip the 2. We don't use the 2 for the height because it's the right-hand side that we use. So the right-hand side height of our first rectangle is 6, and that's going to be this height here for the first rectangle. Right, so we use the 6 height as our right side height. And you can see where this is going. Keep following the pattern. Again, the next area, width of, I think it was 2, right? Width of 2 from 3 to 5. Width of 2 times the height. This time it's going to be 9. In my second one, right? My 9 height, this is going to go backwards like this, is going to be my next height here. Plus, keep going, same pattern. Next width is 3. Next width is 3 times the height. This time the right-hand side of the height is going to be 8 times 8. 8. 3 times 8. This one here. So this one's a little bit shorter than the last one. Right-hand heights, right? You see the right-hand heights. We're using the right-hand side number as the height. Plus, next width is 3 again. Width of 3. And a height this time, right? It's, oh goodness gracious. This time again, it's this rectangle we're using, this 3 here, and the right-hand side is the 4. My height is going to be 4, the right-hand side, 2 times 4, which is this height here. So that one is smaller than before. Sometimes they're larger, sometimes they're smaller, it all depends. Plus my last one, last height, my width, my last rectangle is here, these two numbers, right? My last width is 1, and since I'm using the right-hand side, the height of this rectangle is 0. That's okay. Plus 1 times, in this case my height is 0. It's this side and it's flat. No height at all. And then I add up those together. And that's my right-hand sum. So 2 times 6 is 12, plus 18, plus 24, plus 12, plus 0. Let's see, 30, 40, 54, 62. Is that right? The right sum. $30, 40, 50, 60, no, 60, 66. 66. 30, 40, 50, 66. And so you see the right-hand sum is a little bit less than the left-hand sum sometimes, right? Because we have the 0 here maybe, this is a lot lower, these are maybe a little bit higher. And so we have two different approximations for our area. Two different approximations for our area. Questions about what we did here so far? Found our right Riemann sum, our left Riemann sum. We had a table of values. We used this table here to create our intervals with 5 subintervals. I wanted 5 subintervals. So I used the table to make the intervals 1, 2, 3, 4, 5. I found the widths of those intervals. Sometimes they're different. That's okay. In a table of values, you're given what you're given. You got to use what you got to use. If we had a function here, we could be a little more specific, and we'll do an example of that too. But with the table, we got to use what we got to use. So our widths are up here, and then the heights depend on if we want to use the left side. Right, here's my other right side function. We use the 0. If we want to use the left side, we use the left side number of the table for the left edge for each of my values, right? Each of my heights. For the right side, we use the right number in the table as the height of my f of x's, right? Where am I going? Where are the two choices? Part two choices. Yes, here. And that's what we have with this function here, right? We said we take our heights, all the different f of x function values of those different x values, multiply by the different widths, and then we add all the intervals up, however many intervals we have, we add them all up together and create these rectangles. And remember, there's two choices, left and right, so we decide which one we want to use. Okay. 5 subintervals. And there's two choices, left and right. And we use this table here to determine the heights, right? Because here's my f of x's. Here's all the f of x values, the different heights, and the different graphs here. So that's what we got. Other questions? We're feeling okay. We're getting this. This is doing all right. Finding rectangles, using those to find the area under a curve. Not the most impossible thing. I mean, this is geometry, right? We're doing some geometry here. We're multiplying, we're adding. Pretty straightforward. Not that ridiculous. Yet. Oh, Mitchell, why? Why'd you do that? The other thing they like to do sometimes is, because we know that these two averages are not accurate, right? Because we know these two numbers are not accurate, right? We know that sometimes they're a little bit above, sometimes they're a little bit below, right? We have our function here, like there's a little bit too high, a little bit too low. Sometimes what they like to do is they say, well, what if I took these two numbers and averaged them together? Use L sum and R sum and find an average, and find an average to get a better approximation, to get a better approximation. So we can say the average is 71 plus 66 divided by 2, which is going to be, let's see, 6, 7, 12, 137 divided by 2, which is, what is that, 60, 68.5, 68.5. Somewhere halfway between, right? Halfway between. To get a little bit of a better approximation, sometimes they like to do that. So just find an average, right? Add them up together, divide by 2. And that's maybe a closer approximation, right? Our goal is to try to find as close as we can to the area under a curve. As close as we can. So maybe doing the average of the left and right can kind of even out the rough edges of sometimes it's over, sometimes it's under. So the reason we do this is to eliminate those numbers that are too high or too low and get a better approximation for our area under the curve. You can find those averages. So that's how we can do Riemann sums. We find the function, we find the widths of the function, we find the heights of the value of the function, multiply the width times height a bunch of times, whatever n number of times, whatever n intervals they want, and then add them all up and get our left side or right side, right? Choose which we want, left or right, and we can get our approximations of these sums. But the difficulty, the reason why we do this average one is because, again, sometimes things are, functions are too high or too low. So I want to talk about when do we know if things are, can we tell if things are an overestimate or an underestimate? So let's talk about overestimates and underestimates. Overestimates and underestimates. Let's talk about how we can tell if different graphs are going to be, if we do a Riemann sum, a left Riemann sum, is a left Riemann sum going to be too big, too small? Is a right Riemann sum going to be too big or too small? Depending on the graph, can we tell from the situation whether something is going to be an over or underestimate? For example, if I have the equation y equals, let's do this, the square root of x. Let's do this. This function looks like this, approximately, right? Maybe a little bit sharper, maybe more like this. It's a curve that goes like that. So we have our graph of the square root of x, right? If I used this graph and I had an interval from let's do it here, from zero to whatever, from A, let's call this A to B, right? If I slice this up in 1, 2, 3, 4, 5, 6 slices, right? Here's a height here, here's a height here, here's a height here. Height here, height here, height here, and height, oopsies, height here. So here's my slices, right? When n equals 1, 2, 3, 4, 5, 6, 7. 7 slices. 7 intervals. If I were to do a left Riemann sum, if I did a left Riemann sum, is it going to be too big or too small? If I used the left edge of my function here, the left edge of these intervals is going to be too big or too small. Here's my, let me do the dots here. Here's a dot here. Here's a point here. My heights. These are all my f of x's. My height here, my height here. If I use the left-hand side to create my edges, would the interval be an overestimate or an underestimate? Well, let's take a look. Left side, right? So in my first interval here, I use the left edge here, I have a 0. And then I use the left edge here, I have this height, and then this height, and then this height, and then this height. Consistently, what's happening here? Well, I am consistently missing pieces. Consistently. Did I spell consistently? Missing pieces. Consistently missing pieces. I'm always underestimating because of the nature of the graph. Because the graph is curved in this particular way, because the graph is curved, consistently arcing down, right? This is a concave down, increasing concave down function. Because of the increasing concave down nature of this equation, my left edge is constantly, forever, going to be an underestimate. It's not going to be too big, it's going to be too small. It is an underestimate. Underestimate because of the curve. Because of the shape of the curve. It's going to be an underestimate. Whereas if I try to do my right sum, my right side is always going to be too big. Always going to be too big. Right? My right side is always going to be too. It's consistently too big. My right. I should label these. You may not have colors. Right and left. Left. So the right sum is too big. So it's an overestimate. Again, because of the nature of the curve, because of the shape. Because this is a concave down, increasing function. The reason why I can tell it's over or under is because it's going to be that way every time. If it was more wiggly, if it was like it went up and then down, then up again, sometimes it's over, sometimes it's under, I cannot tell. But because it's consistent, every time it's too big. Every time. Then I know it's an overestimate. Every time, if it's too small, I know the entire thing is going to be an underestimate. Consistently every time. Because of the shape of the curve, because it is consistently concave down, increasing. So you can tell kind of from the nature of these curves how things are going to shake out, right? So if I have like a graph that looks like, we'll do a couple examples. If I do a graph that looks like this kind of curve, if I have this curve, which one is going to be, is a left going to be an over? Left. Which one's going to be over, which one's going to be under or right? From A here, from A to B. Which one's going to be too big, which one's going to be too small? Think about the lines here, think about the edges. Left side, yep, that's very good. Left, good Jessica, good person. Left is going to be too big, an overestimate. And the right side is going to be an underestimate. So if we look here at the left side, if we try to draw even one of them, we can tell immediately that's too big, right? And the right side we can tell is going to be too small. Okay, what about this curve here? Another example. What about one that goes like, let's see, how am I going to... That, we have that. What did I do already? All right. What about this? Whoopsies. This curve here. What about left and right here? From A to B. Which is over, which is under. Is the left side too big? Is the left side too small? Right going to be too big? Right going to be too small? What about the left one? Let's talk about the left one. Is the left going to be an overestimate or an underestimate? If I use my left edges, what's going to happen? Left side, if I go out, each time I use my left edge, I'm going to be a little bit too big, right? So here we have another overestimate on the left side. And the right side, we're going to be consistently missing pieces, right? Consistently missing. It's going to be under. So both of these functions are decreasing functions. So this is the situation anytime you have a function that strictly decreases, the left side will always be overestimating and the right side will always be under. Any function that is strictly decreasing. Decreasing here, it's decreasing here. It's only getting smaller, only getting smaller. So when your function is decreasing, your left side is going to be over, your right side is going to be under. No matter if it's decreasing this shape or this shape, as long as it's decreasing, it's going to have these features. Increasing is the opposite. Increasing, your right side is over and your left side is under. Increasing functions are opposite. Will always have this result. Increasing functions are opposite. Increasing is opposite. Right, so if you have a function that is increasing like this from A to B, again, your left side is always going to underestimate now. Left side is under. Left is under. And the right side is going to overestimate. So decreasing, you're always going to have, and you can just visualize it. If it says decreasing, just draw a decreasing function. If a graph says this function is strictly decreasing, you know it's going down the entire time. You know that the left edge, right edge is going to be consistent the same time, the same way every time. It's always going to be the left is too big, the right is too small. And if you can't remember this, just draw it. Draw a decreasing function. Okay, here's a decreasing function. If I'm using the left edge, that's going to be too big. That's too big. Okay, left is over. If it's increasing function, left side, oh, that's going to be too small. So just draw it out for yourself and see if that will help you visualize what is happening in the situations. All right. Questions, concerns, worries? So, a little bit of introduction to Riemann sums. You have a handout to work on over the weekend. Go over it on Monday. Let me show you that, and then we'll be done for the day.